Okay, greetings everyone. Thank you for joining our side event discussing the U.S. contributions to Arctic research, applications, and decision support. My name is Michael Falkowski, and I'm a program manager at the Earth Science Division at NASA headquarters in Washington, D.C., and I'll be moderating today's side event. Today we will have a series of talks targeted on highlighting how U.S. data models and science enable Arctic monitoring, understanding, and prediction, with implications for global climate change. Today's presenters are coming to us from a variety of U.S. agencies and institutions that are all actively involved in different aspects of Arctic research, applications, and decision support. Today's first speaker is Larry Hensman, and he's the Assistant Director of Polar Sciences within the White House Office of Science, Technology, Policy, and the Executive Director of the Interagency Arctic Research Policy Committee. As a professor at the University of Alaska Fairbanks and director of the UAF International Arctic Research Center from 2007 to 2015, he conducted hydrological and meteorological field studies in the Alaskan Arctic continuously over 35 years, while frequently collaborating on complementary research in the Russian and Canadian Arctic. And so with that, I'll turn it over to the people in Glasgow to start the video for Larry.
Hello, my name is Larry Hensman. I'm the Assistant Director of Polar Sciences at the White House Office of Science and Technology Policy. And today I'm going to be talking to you about the consequences of a changing climate to Arctic societies and ecosystems. This is really an important time for communities that must adapt to a rapidly changing climate and environmental conditions. Such changes will influence decisions related to infrastructure, transportation, and management of natural resources. Our communities and our nations are facing a great many uncertainties, and we will be relying upon scientists and engineers to help us make informed decisions and to help us make good policies and to help people in cold regions continue to thrive. From 1971 to 2019, the annually averaged Arctic near-surface air temperature increased by 3.1 degrees Celsius. 3 times faster than the global average. Arctic permafrost has warmed by 2 to 3 degrees Celsius since the 1970s. At many of the colder permafrost sites, the rates of warming over the past 20 years have been greater than any time since 1979. The seasonally thawed active layer has grown deeper at many sites since the 1990s, and landscape observations indicate that permafrost is thawing all across the Arctic. The presence or absence of permafrost exerts a dominant control on important surface characteristics, including soil moisture, surface temperature, vegetation type, trafficability, and landscape stability or vulnerability. So changes in thermal state or extent can substantially affect civil society and ecosystems. The understanding of the interdependence of these processes provides useful insight for projecting how ecosystems, regional climate, and even watershed hydrology may evolve as the climate continues to warm. Such understanding is essential for community planning, resource development, infrastructure construction, and most other activities of relevance to society that have a 50-year or longer expected lifespan. We do know the direction of climatic and environmental trends. We know the drivers, and we have a good understanding of the interactions. This graphic shows the simulated evolution of Alaska ecosystems over the next century. It is not difficult to hypothesize what the future will look like. However, it is difficult for us to predict with great accuracy when certain changes will occur. We do know they are coming, perhaps with decadal accuracy. So it is only prudent to look ahead, distant in the future, and try to perceive what that design endpoint may be. We need to consider the range of conditions our infrastructure and our communities and our ecosystems are likely to experience. We need to plan not just using the current conditions, but for a distant tomorrow. Considering a longer-term perspective without holding our expectations of the environment fixed, we can better help our communities and our nations utilize our limited resources, enhancing the resilience of our communities and the sustainability of our environment. Permafrost underlies nearly 24% of the terrestrial regions of the Northern Hemisphere. So this is a very large problem that will only become worse in coming years. Minimizing disruptions to civil society and degradation of ecosystems must include efforts to mitigate the ongoing climate warming. Concurrently, we need to better design and construction techniques that can slow or withstand permafrost degradation, or include maintenance technology that allows inexpensive renovations. Arctic research can contribute to making our communities more sustainable by developing new techniques, new technologies, or by offering insights into appropriate design criteria. Scientific and technological advances implemented now will make our communities more resilient in the decades to come. Climate change has initiated a myriad of environmental changes in the Arctic. Unfortunately, many of those contribute to greater frequency and severity of wildfire. The 10 warmest summers of the last 100 years have occurred since 1975, while the 10 coolest summers of the last century occurred before 1975. We are also seeing a progressively shorter snow cover season and a progressively longer fire season. The longer thaw season and warmer temperatures are also leading to degradation of permafrost, which enhances internal drainage and thus leads to drier soils, all of which lead to more fire-prone conditions. In recent years, we can see a substantial increase in the frequency of the fires and increases in the amount of land burned. In the United States, 16 federal agencies are collaborating to develop the next federal Arctic research plan. The developing plan will facilitate collaborations among federal agencies, but also with non-federal researchers at universities and foundations, with international researchers interested in Arctic science. 4 policy drivers guide this research: well-being of Arctic residents, stewardship of the environment, security, and understanding of Arctic to global systems. These represent the long-standing US policies toward the Arctic and ensure continuity of the US scientific priorities, commitment to our collaborators, and consistency in the execution of our research activities, including respecting community members and honoring the environments we study. These are 2 of the goal statements for the draft Arctic Research Plan, which will be implemented starting in January of 2022. If you're familiar with the current Arctic Research Plan, you'll note a substantial change in the approach. The current plan is much more focused along disciplinary lands, seeking to expand our knowledge of physical and biological processes and the role of the Arctic in global climate systems. These challenges pull together our collective knowledge of the Arctic processes to make communities more sustainable, healthy, and economically viable. Priority Area 1 is focused on improving community resilience and well-being by strengthening the research and tools to increase understanding of interdependent social, natural, and built systems in the Arctic. Priority Area 2 will enhance our ability to observe, understand, predict, and project the Arctic's dynamic, interconnected systems and their linkage to the Earth system as a whole. Priority Area 3 addresses the Arctic's natural, social, and built systems to promote sustainable economies and livelihood. Priority Area 4 aims to improve the quality of life through an understanding of disaster risk exposure, sensitivity to hazards, and adaptive capacity. These goal statements are more integrative and more interdisciplinary. They grew from the current and prior Arctic research, building collaborative communities of practice to take on higher order challenges and requiring more collaborations and more contributions from a wide array of scientists, engineers, and community planners. The Arctic Research Plan is responsive to President Biden's priorities. This plan is well aligned with priorities on economy and healthcare. There's also emphasis on the administration's priorities related to climate change, racial equity, and tribal consultation. This plan specifically responds to the President's executive order on tackling the climate crises at home and abroad, the executive order on advancing racial equity and support for underserved communities, and the presidential memorandum on tribal consultation and strengthening nation-to-nation relationships. Thank you for your attention today and for your interest in efforts to address the consequences of this changing climate. There is much to do, and we are blessed to have strong researchers taking up these challenges. We can make our best progress and achieve the most optimum outcomes when we have many collaborators all contributing their expertise and resources to resolving our common challenges. Thank you.
All right, thank you, Larry. So we'll transition right away to the next speaker, who is Sandy Starkweather from the National Oceanic and Atmospheric Administration. Sandy is the Executive Director for the U.S. Arctic Observing Network, where she advances U.S. agency participation in the International Arctic Observing System. With a joint background in engineering, earth science, and science policy, Sandy has worked in a consulting, engineering capacity, university research, and project management and planning in the Arctic.
Good morning. I'd like to thank the organizers of the COP26 Cryosphere Pavilion for including the important topic of Arctic observing networks in today's discussion. My name is Dr. Sandy Starkweather. I'm a research scientist at the University of Colorado and also a Noaa, National Oceanic and Atmospheric Administration affiliate, on whose behalf I lead interagency efforts in support of U.S. Arctic Observing Network Partnership Development. And I'm simultaneously serving as the chair of Sustaining Arctic Observing Networks, or SAON, our international body with the same emphasis. I'll provide some more details on SAON throughout the course of these slides. But I'd like to start at the highest level by saying, why do we need Arctic observing networks? We understand through discussions at the Cryosphere Pavilion and that discussions that have been happening for the last couple of weeks at the COP26 that Arctic changes are unprecedented. The images on the right depict a few of these concepts that we're seeing direct impacts on the cryosphere, such as loss of sea ice, loss of land ice, thawing of permafrost, which also have knock-on effects in the form of increased storm surges, for example, in coastal communities that had typically been protected by sea ice. And in the bottom image, we see a fisheries vessel and are very candidly aware that the changes to the environment that we're seeing in the Arctic are having knock-on effects in our ecosystems. Observations inform the actions that we need to take in the face of these changes. But at present, our observing networks in the Arctic are inadequate to informing these changes. And I'll shortly turn to more details on why. But at the highest level, we're looking at systemic issues related to technology, access, and planning at the global, regional, and local scales that are impeding our progress. So a few examples of what the sparse networks in the Arctic look like and some of the reasons leading to these conditions. Starting with the observations of the ocean, and I'm providing here an example of the Global Ocean Observing System and its network of autonomous technologies that you see distributed across the global oceans. And what's immediately obvious in this image is that the Arctic observations are nowhere near the level of intensity that the rest of the ocean systems are being observed at. And some of these issues are related to the physical constraints of the Arctic. For example, the Argo floats that are the backbone of the Global Ocean Observing System are not able to perform adequately under sea ice conditions. But we also have marine access constraints for the deployment of instrumentation. Some of these are physical constraints, some of these are more policy-oriented constraints. And so there's a real need for technology and access development to change what you see in this map. Another example from the standpoint of the Global Atmospheric Watch System, we see, again, a sparsity in the types of observing infrastructure that are where you see very high density in, of course, wealthier nations, in higher populated areas, and in mid-latitudes, And again, in the Arctic, very sparse networks. In this case, many of the atmospheric instrumentation require fixed infrastructure. There's not as much autonomous technology, but it is a growing field supporting atmospheric observations. And so there's a need for both, again, technology development, but also infrastructure development to support networks like GAW. An example from hydrology, and this is just showing a map of the United States with the inset of Alaska at the bottom, where we see that our stream gauge networks in the United States, again, very nice density in the lower 48 in higher populated areas. And when we get into the state of Alaska, we see very low density in this network. There's not a very extensive road system in the state of Alaska. There's also not a very extensive telecommunication system. And so here again, we return to these themes of needed infrastructure development in the form of telecommunications, but other forms of access as well. And for context, I'd like to share this depiction where Alaska is actually shown to scale on the map of the United States. And here we can recognize that the situation is much more exacerbated than is shown in this image. Last, and I'll run this small video showing changes in snow cover on a monthly basis over several years. And what I'd like to discuss in this slide is that satellites are an incredibly important capability for addressing these monitoring gaps in the Arctic. You can see really nice reach up into these regions with other kinds of access issues. But that persistent line that you see tracking the seasonal snow cover is not the snow cover itself. That is a limitation of imaging satellites during polar darkness. They can't see the ground the same as we can't see the ground during polar darkness. And persistent cloud cover, which we see very often in the Arctic, can also provide some constraints on what's possible with satellite capabilities. So for a variety of reasons, returning to our previous slide, that are technological in nature or related to infrastructure and access, infrastructure and policy, I would say access issues. In addition to these issues, what we recognize is that there's also some planning issues that are impeding our progress. And so that is the type of issue that SAON was created to address. So Sustaining Arctic Observing Networks intent is to unite many partners together in the planning of Arctic observing networks and data systems in order to make progress on issues where planning is needed. And so this includes Arctic and non-Arctic countries, Indigenous peoples organizations, academia, industry, and so on. We were created as a joint body of the Arctic Council, from which we draw our policy-oriented mandate, and the International Arctic Science Committee, from which we draw our scientific mandate. What has been increasingly recognized since SAON was created, I'll start with from the policy sector, is that while facilitation and convening is much needed, what's really needed is a planning process. And so the Arctic Science Ministerials, who've met ministers who've met three times since 2016, have encouraged SAON to play a more active role in the design and implementation of the needed system. From the grassroots end, the biennial Arctic Observing Summit has similarly called upon SAON to show a more enhanced role in network planning. So SAON has responded to these calls by initiating what we're calling our Roadmap for Arctic Observing and Data Systems, which is meant to be a planning process that operates at the meta level to bring existing planning processes together through a lens that supports shared benefit in the Arctic. And so the concept, which I'll briefly touch on here before we close, is something that cues off of the essential variable planning approaches of the global networks but it extends it into key Arctic communities to develop what we call a shared Arctic variable lens. So in any essential variable process, what we're doing is we're parsing the greater system into smaller units to organize communities of practice around methodologies and systematic approaches to better network our observations. And so I'll walk you through our concept as it's been developed thus far. So as I mentioned, the essential variables of the global networks were really the inspiration for this work. But we also note that they've got limitations in terms of their implementations, as we've just seen. And so in order to improve and enhance their capabilities, we know that we need to bring in partnerships from Indigenous communities and recognize that there are Indigenous-led observing strategies that support Indigenous identified benefits that bring these partners to the table in support of their community needs, but also bring their capabilities to the table, and that we can work to link these capabilities to those of the global networks. Similarly, we have many regionally identified science and decision-making needs and observing strategies, for example, such as those that are supported through Arctic Council deliberations. And so our shared Arctic variable concept is meant to bring these groups to the table in support of broadening benefit and broadening implementation approaches. So I'll just return to this final slide to say, why do we need SAON's roadmap or the ROADS process? SAON has been given a mandate to facilitate planning in this space, and ROADS, which I've just briefly touched on here, is its partner development tool to extend the impact of global networks in support of shared benefit and also the equitable inclusion of Indigenous people. Thank you.
All right, thank you, Sandy. Transitioning to the next talk now, which will be given by Robin Bell. Robin is a research professor at the Lamont Doherty Earth Observatory at Columbia University and past president of the American Geophysical Union. Bell's research accomplishments emerged looking historically at Earth's large ice sheets on our planet with the goal of understanding how they work and how they will change in the future. She is motivated by the goal of enabling coastal communities around the globe to develop scientifically informed strategies to respond to changing sea levels.
Hello, my name is Robin Bell. I am a research professor at Lamont Doherty Earth Observatory, part of Columbia University's Climate School. Today, I'm going to talk to you about how the ice in Greenland is changing and what are the global lessons we know from learning about the changing ice and how to work with communities who are adapting. Greenland is a large subcontinent. If you flew from North America to Glasgow, you probably flew over. Large, white, expansive. It extends from, if we were to drop it on North America, from New York City to south of Florida. A big piece of ice. If you fly over it in an airplane, and this is what you would see if you looked out the window, today you would see bathtub rings. And that's that. What you're looking at here is a glacier flowing out of that large body of ice. And you can see that light gray bathtub ring, basically a part of the landscape that's been exposed recently because of the loss of ice. We know more than just the bathtub ring evidence. We know from NASA's comprehensive missions that we know that the ice sheet's moving faster. It's getting lower, that's the bathtub ring, and it's losing weight. So those are three independent observations of how the ice sheets are changing. I could show you either Greenland or Antarctica, but here we're just going to look at Greenland. One of the wonders is we used to just look at those glaciers and think we could see them move and watch individual crevasses. But due to the beauty of satellite observations acquired over the last 2 decades, we can now track these rivers of ice. And that's what we're looking at in this movie. You can actually see the tracers of ice moving where red is slow, maybe a meter or two a year, and purple is up to tens of to 1,000 meters a year. So you can see the ice flows from the middle slowly and then converges into these river-like structures, what we call outlet glaciers, or sometimes ice streams, as they flow out. And what we've seen is this velocity double over the observed record in some key outlet glaciers. Now, what's remarkable, remember this is just one observation, is we're also capable of seeing, other than just that bathtub ring, using satellites. And these are examples now zooming in again and looking at Greenland. This is where NASA has sent up satellites, ICESat-1 and ICESat-2 now. Those tracks are showing you where on the ice sheet the lasers from space have shot down. And again, what you're seeing, what you're going to see over that time period, how significantly that ice surface has dropped. And what you can see here is you can see how the edges have dropped a lot. Again, remember we saw the bathtub ring at the edge. And now we can look over time and we can see that that mass loss pulses over a season as the snow falls in the winter and builds back up in some places. But you can also see the red along the edges growing as the ice sheet drops and drops and drops, on the order of meters per year around the edge. So that's the second very clear signal that the Greenland ice sheet's changing. So we see it going faster and we see it getting lower, and not just in one outlet glacier, but all along the rim of Greenland. The third measurement is actually how much does the ice sheet weigh. This is done by a pair of satellites chasing each other in space and measuring what the ice sheet weighs. And what you can see, again, if you're looking at the left, you can actually see the yellow growing along the edge. Remember, this is the same place that we saw the ice sheet speeding up and getting lower. And you can see the red marks growing and growing along the margins. And that started in around 2002. And you can see that again, just like the velocity speeding up, the elevation dropping, we can see this third independent measurement of the ice surface losing mass. So we can say Greenland is losing mass all around the edges. So 3 independent observations, really compelling that Greenland is losing mass. What are the consequences? This is a snippet from a 2008 Scientific American article I wrote. But really the important thing is there's a lot of ice in Greenland. The ice in Greenland, if it were all to melt, would rise sea level globally, something on the order of 24 feet. And this is kind of what it would look like in Florida if that all melted, and it simply went up everywhere. What's the evidence for change? This is one of my favorite images. It's from Noaa. And what it just shows is where places we have tide gauges in the water, and that we can see that around the globe, almost everywhere, those arrows are going up. And those arrows are going up, indicating sea level is rising. Some places it's falling, but that's mostly because the land is bouncing back. But the global impact is clear. But what does this mean to communities? We've recently launched on a program with support from the National Science Foundation on how we look at those places where sea level is changing dramatically. Turns out it's changing dramatically along the coast of Greenland because it's one of those places where the land is bouncing back up. And what we found is that we need to work with communities to look at their observations and predictions of how sea level is falling. We need to figure out how to connect their eyewitnesses' report of how sea level is changing to what's going on in their local habitats, what's going on with their infrastructure, and what's going on with their ability to hunt and fish. So we've been really trying to bring this understanding of how the globe works and even the complexities of the land bouncing back, actually causing the sea level to fall around Greenland, to communities to understand how they're going to move forward with development, and a sustainable future. So this just gives you a quick snapshot of if we put a GPS, or even if you just left your phone on the edge of Greenland long enough, you'd actually see it bouncing up. And what we're doing is trying to improve the future predictions of how sea level is going to fall. We're hoping that this will be a model for how to work with communities to adapt to climate change and changing sea level around the globe. We're working with 4 communities where there's a very different signal and very different types of communities, but we're trying to engage them through the entire process. These are communities where in the future we expect to see maybe minor sea level rise to possibly 3 meters of sea level fall. You can imagine if you're a community that depends very much on your maritime abilities to fish, hunt, and move by boats, 3 meters of sea level drop is going to have significant consequences. We've already found that sharing and engaging the communities in the planning has both benefited us, where we've learned places already they're seeing islands emerge and places they can no longer travel routinely because of the land rising. Or here's a fisherman who's been able to use the data to actually improve his ability to fish. This is the type of work we're doing, engaging young Greenlandic scientists to go map around their communities, putting cameras overboard to understand how the habitats are changing and what these future will bring. We've also tried to bring the science directly. This is looking at how the ice will change, remembering the ice is flowing and dropping, and bringing that knowledge into the communities. So where does that leave us? That leaves us with a sense of hope that we're in this unique place where we have this view of how the ice sheets are changing, but we also have the opportunity to learn, to share that knowledge, and to build a future based on that knowledge. Thank you.
All right, thank you, Robin. Our next speaker is Andrei Petrov, who is an associate professor of geography and geospatial technology in the Department of Geography at the University of Northern Iowa. Andrei directs the Arctic Social and Environmental Systems Research Lab, as well as the Program in Research and Outreach in Geography between Russia and the United States. So with that, we will start Andrei's talk.
My name is Andrei Petrov. I'm director of the Arctic Center at the University of Northern Iowa. The subject of my presentation is climate change and its impact on Arctic peoples. First of all, let's remember to realize that there are 4.5 million Arctic residents. As correctly stated in the Arctic Human Development Report, although sometimes and very often we consider natural resources as the main treasure of the Arctic, the true treasure is its people. Arctic people live in various circumstances in urban and rural communities that are scattered across different regions. So it's important when we talk about the impact of climate change to articulate that there are a variety of different kinds of experiences across the Arctic related to climate change. It's also, of course, critical to realize that among 4.5 million people, Arctic residents, there are hundreds and thousands of indigenous peoples. They are very diverse, that live for millennia in all parts of the Arctic. In Alaska specifically, which represents about 1/5 of US territory, is a homeland for about 229 indigenous peoples and 20 different linguistic groups. So it's very diverse experience as well. And whether it's interior or coastal Alaska, there will be very different kinds of things that communities are dealing with as it relates to climate change. But no matter where we are and where we look, climate change in the Arctic, its impacts must be understood from a socio-ecological system perspective. There is no better illustration of this as done by the Inuit Circumpolar Council Alaska, that represents the socio-ecological system for the Inuit as the puzzle. And one segment of the puzzle, if it's taken away or affected in any way, the entire ecosystem, the entire socio-ecological system collapses. And that includes both social components and natural components. So it's very important to have a focus on the systems approach here? Well, if we start by looking at the key U.S. contribution to understanding Arctic people's experiences with climate change, we have to remember that Arctic communities have been a priority in successive research plans by both U.S. Arctic Research Commission and by the other agencies in the United States. There have been major investments by the National Science Foundation to study those experiences as a part of the Navigating a New Arctic program that in the last few years invested about $120 million in Arctic research. The key initiatives, there's plenty of those, but something that's important to highlight, for example, is ILOCA, that is for years working with communities to collect community data on climate change. There are key institutions in Alaska that conduct research that is dealing with adaptation and impacts of climate change. It includes University of Alaska and, of course, ICC Alaska, which is Inuit Circumpolar Council Alaska. It is important that in the last few years, there have been strong push to refocus Arctic research in the United States on community-driven, locally based and capacity-building projects and provide funding to community organizations such as COEREC, a very influential COEREC letter has been written in 2020 that has characterized and has proposed a new way for Arctic science to work with Arctic communities. Since then, there is considerable enhancement of indigenous engagement in knowledge co-production in the United States Arctic science. But if we look at the climate change and what we know about the impacts, and we specifically zoom into Alaska, we'll see there's a variety of these impacts, whether they relate to caribou population dynamics or changing migratory patterns of fish or sea mammals or birds, whether it relates to the wildfires. There is a variety of things we could look at. So for the shortness of this presentation, I just focus on food insecurity, permafrost hazard, village relocations, and wildfire threat. Food insecurity, of course, is a cornerstone of indigenous people's well-being. When we talk about the impacts of climate change, we see the variety of dimensions of that. As you can see in the top right corner, there is a depiction of the food security concept from the Inuit Circumpolar Council Alaska, which is eloquently describes it as a drum, and this was centered on food security with other important elements around it. So as we can see, increased uncertainty of access and availability across time and space of the harvest and resources, nature resources, is the key impact on food security. That relates either to novel ice dynamic and variability, or to changing migration patterns or shifting seasons that prevent indigenous communities from having access or availability of traditional food items. And that trickles to other things like cultural sustainability and other important elements of indigenous cultures and communities. There are other things that happen in the Arctic that have impact on food insecurity. It's catastrophic unusual events such as rain and snow, fires, or temperature swings. It's arrival of invasive species. It's pollution that's generated in other regions that percolates and comes into the Arctic. And very importantly, in most of these circumstances, there is lack of decision-making power on the part of the communities, and especially indigenous communities, to deal with that outside of their lands. And that is a serious issue that we all need to collectively work to alleviate some of that in the future. The permafrost hazard is another important problem that is prevalent across the Arctic. The permafrost in the Arctic is thawing rapidly, and it is having impacts on both large cities and small communities. We could see the depiction of the damaged ice cellars in Utqiagvik, Alaska, that prevents local communities from storing their food, all the way to collapsed buildings that are being found in a variety of cities across the Arctic. By 2050, 1/3 of the Arctic infrastructure will be under the high risk of collapse, and that's really a serious concern that of course, is true for urban infrastructure, industrial infrastructure, or in many ways, infrastructure related to traditional livelihoods. Another important problem in Alaska is village relocations. 12 Alaska villages have been actively exploring relocations, and some already on the move. It is a problem related to collapse, the shoreline collapse and flooding for the most part. About 3,500 residents are affected, and cost of moving each village is about 80 to 200 million. So it's a major investment, it's a major problem, it's a major community issue that is collaboratively resolved with communities, knowledges, and science. Finally, the wildfire threat have been increasing in recent years, as you can see on the chart. Both the spread and intensiveness of fires have been growing. It represents a real threat to communities in terms of personal safety, life, infrastructure, and property displacement, health, and access to subsistence. In addition to that, since those fires take place in very remote areas, it's a very high cost of suppression and recovery. At the same time, we need to emphasize that while there's a lot of impacts and vulnerabilities that are observed across communities in the Arctic, there are sources of resilience to climate change and adaptation. First of all, they're embedded in indigenous knowledge. Arctic indigenous communities possess experience-based indigenous knowledge developed for millennia. Indigenous knowledge provides foundation for individual and collective well-being of past, present, and future generations. It's a knowledge system that holds its internal value and methodologies, and that is a separate and standalone system that works and could be engaged by working with scientists to arrive at conclusions and policy actions that actually have legitimacy. Indigenous knowledge empowers communities to significantly advance our understanding of and response to climate change. And overall, indigenous knowledge, self-determination, and co-production with Western science will create sustainable solutions for the Arctic. And if we are embarking on this, it's important to consider changing sustainable development goals for the Arctic to include important issues for Arctic communities, especially indigenous communities, such as sustainable governance and human and indigenous rights, such as resilient indigenous societies, livelihoods, and knowledge systems, such as life on ice and permafrost, equity and equality, access to nature resources, and investment in youth and future generations. Thank you.
Okay, thank you, Andre. The next speaker we have today is Leslie Ott, who is a climate scientist at the NASA Goddard Space Flight Center, and she possesses over 20 years experience studying air pollution and greenhouse gases. She currently leads the carbon group within the Global Modeling and Assimilations Office, NASA Center for Understanding Contemporary Weather and Climate using a family of advanced Earth system modeling tools. Her work focuses on using a combination of satellite data and numerical models to better understand the sources and sinks of greenhouse gases and how the processes that control them may change over time. With that, we will transition to Leslie's talk.
Hi, my name is Leslie Ott, and I'm a climate scientist at NASA's Goddard Space Flight Center. Today, I want to talk to you about the Arctic carbon cycle and some of the ways we're trying to measure that with our satellites and study it with our Earth system models. So before we get started and dive into the Arctic, let's start with a very brief introduction on what the carbon cycle actually is. So carbon dioxide is the most important greenhouse gas released by human activities, the main driver of climate change. And it actually cycles naturally between the atmosphere, land, and oceans. But over the past few centuries, people have disrupted these natural cycles by burning fossil fuel that's stored very deep below the surface and effectively injecting a lot of carbon into the atmosphere via combustion. The other critical pieces of the carbon cycle are the ocean-land exchanges. In global terms, that collective sink takes up about half of human emissions every year. And this is a hugely important service because otherwise we'd be seeing climate change progress much more rapidly than it is already. But one big concern that scientists like me have is how long all of our plants and our oceans can continue to absorb all of this carbon. So in addition to carbon dioxide, scientists are tracking the world's second most important greenhouse gas, and that's methane. Methane is emitted by a different mix of sectors, including things like fossil fuel production, agriculture, and waste disposal. But another very large source of emissions is natural, and that's methane coming from the world's wetlands. In addition to emissions from human activities, scientists are also really concerned about changes in the natural emissions because we know that they're very sensitive to temperature. So the warming that we're seeing associated with climate change could actually increase global wetland emissions, which would be a positive feedback that helps accelerate climate change. So we've talked about carbon at the global scale. Now I want to zoom into some of the things that make the Arctic special. First, you may have already seen this, but it's the temperature change relative to the middle part of the last century. And we know that changes in surface temperature are several times greater in the Arctic compared to the global average. And we also know that those large swings in temperature are already having profound effects on that land, air, water, and ice throughout the region. So understanding how Arctic ecosystems are changing and how that affects the delicate balance of carbon sources and sinks across the planet is a really important preview of how warming may affect all of us. The other major factor that is unique to the Arctic is the presence of permafrost, or perennially frozen soil. Northern soils are also really special because they're incredibly rich in carbon. They contain, trillions of metric tons of carbon, which is about double the burden that we have in the atmosphere right now. And to limit greenhouse gases and temperature increases in the future, we really want all of that carbon to stay where it is right now, below the ground. But when we combine those couple factors, the frozen soils with the warming that we just saw, we're starting to see more thawing of the soil, and that can promote microbial conversion of carbon into greenhouse gases. So one of the key questions you're going to hear more about a little later on is what's happening to all of the carbon that's stored in our permafrost, and how is that going to affect the overall carbon balance of the Arctic now and in the decades to come? So now I want to show you a few different types of observations that NASA makes that help scientists understand the Arctic carbon cycle. So right now we're looking at a movie that shows the color of our land surfaces and our oceans. This is coming from two instruments that NASA operates called MODIS, and they together provide a 20-year record of life on land and in the oceans. So on land, the colors that you're seeing are telling us how green the vegetation is. In the Arctic, long-term records like this are really critical in helping us understand how ecosystems and their ability to store carbon has changed over time. And in some areas that had been dominated by grasses, we're starting to see encroachment of shrubs and trees, different types of vegetation. In other forested areas, we're starting to see some evidence of browning due to more frequent droughts and changes in wildlife activity. So being able to keep tabs on all these changes from space is critically important, because the net carbon balance of the Arctic is the sum of all these little small scale changes. So for example, replacing those grasses with shrubs means one area might absorb more carbon, but damaging trees and forests might mean that we lose the ability to absorb carbon somewhere else. And we have to add all those vegetation changes up with the potential for increased release of greenhouse gases from soils and our wetlands. I also want to note another thing you're seeing here, which is that the northern oceans actually play an important role in the carbon cycle, because carbon dioxide is absorbed both by water itself and by tiny plants in the water called phytoplankton. These same satellites, these same MODIS instruments that help us track life on land, are also helping us track changes in the ocean by measuring ocean biology, so that we can better understand the roles that our ocean are playing in the global carbon cycle and the Arctic carbon cycle. The next measurement I want to talk about is a fire. In this animation, we're looking at the intensity of fires all over the world from NOAA's weather satellites. Now, fires are a really important part of the carbon cycle because they can reduce the capacity of a forest to store carbon and directly release greenhouse gases into the atmosphere. Fires in areas with those carbon-rich soils that we talked about are a particular concern because they can actually smolder for a really long time, for months at a time, and release soil carbon to the atmosphere. So we're particularly concerned about fires in the Arctic because climate change is causing increase in several of the extremes that can lead to fires. In some areas, we're seeing more pronounced droughts that can dry out vegetation, making it burn more efficiently. And we're also seeing increases in the frequency of thunderstorms and lightning at high latitudes, something you probably don't think as much about. But that combination of factors could result in more fires, which alters the carbon balance and even affects what kinds of plants will make up high latitude ecosystems in the future. Because many of these fires are happening in remote regions, satellite data like these are providing a really critical tool to scientists for understanding their impact. And in more populated areas, managers on the ground can actually use these data to help fight the fires. So this is one last critically important observation that I want to highlight, and that's of atmospheric carbon dioxide coming from NASA's Orbiting Carbon Observatory 2, or OCO2 for short. Now, OCO2 estimates the total number of carbon dioxide molecules from Earth's surface to the top of the atmosphere using information that's contained in reflected sunlight. And this is actually a really tough measurement to make. It's so tough that NASA has only been making this for about 5 or 6 years. But it's given us the most complete picture of atmospheric carbon dioxide that we've ever had. But still, I want to note some important gaps that if you're focused on the Arctic, you're probably seeing. OCO2 requires clear sky, sunlit conditions in order to make measurements, but the Arctic is dark for a good portion of the year, and we also have a lot of clouds. So that means we don't have nearly as many direct observations from these kinds of satellites as we'd like. And that means we have to get creative to find ways to fill in gaps by setting up surface station or flying airplanes, or even working to build satellites that can observe greenhouse gases in the dark in the future, which is an important future direction for NASA and the rest of the world's space agencies. So I want to end on one last science contribution that NASA makes to stitch all of these data sets together to understand how the Arctic is changing today. This is a model simulation of carbon dioxide. It's actually combining all the observations that we just saw on greenness, fires, ocean color, and carbon dioxide concentration to create this incredibly complex three-dimensional view of the movement of carbon through the atmosphere. Models like this are really important for getting the most out of our satellite observations because, as we just saw, sometimes we have trouble measuring the Arctic, and having models that can take an observation that's observed downwind and track it backward, sometimes that's the best constraint that we have on greenhouse gas emissions in those regions. Also, these types of models can integrate all of the lessons that we're learning in order to be able to predict how the Arctic is going to change in the future. And that's the kind of actionable information that environmental managers and decision makers need to help all of us navigate a warming world and to understand how changes in Arctic carbon are going to affect the carbon balance of the entire planet.
All right, thank you, Leslie. And finally, we'll be transitioning to our last talk in this side event by Charles Miller. Chip is a scientist at the NASA Jet Propulsion Laboratory. He has over 20 years of experience leading satellite and suborbital projects for NASA Earth Sciences. He helped develop the Orbiting Carbon Observatory, OCO, concept for space-based CO2 measurements. He has served as OCO Deputy PI and Science Team Lead. He's a principal investigator of an airborne science experiment the principal investigator for an airborne science experiment that revealed new insights into the sensitivity of the Arctic carbon cycle and to climate change and disturbance. He's principal investigator on several other projects that link permafrost vulnerability and changes in the Arctic sea ice regime to Arctic ocean biology and biochemistry, and he currently serves as Deputy Science Lead for NASA's Arctic Boreal Vulnerability Experiment. With that, we will move to Chip's talk.
Ladies and gentlemen of the 2021 United Nations Climate Change Conference in Glasgow, thank you very much for your interest in Arctic Methane and Permafrost Challenge, a NASA ESA collaborative community initiative. My name is Charles Miller, the NASA lead for this initiative, and I speak with you today on behalf of my ESA counterpart, Diego Fernandez Prieto, and the AMPAC science team. You may find more information on AMPAC at the NASA and ESA websites included below. Permafrost, the perpetually frozen soils particularly associated with boreal forests and tundra of the Arctic region, have accumulated over tens to hundreds of thousands of years and cover approximately 25% of the northern hemisphere land area. The largest concentrations of continuous permafrost, dark purple in this map, are found in Siberia, northern Alaska, and northwestern Canada. The cold, wet conditions that have historically characterized permafrost environments effectively prevent the decomposition of any dead plants or animals, and vast stores of organic carbon have accumulated in the permafrost over time. Surveys and data synthesis efforts led by Gustav Hugelius and co-workers suggest that more than 1,100 billion metric tons of carbon, or 1,100 gigatons, are buried in the top 3 meters of Pan-Arctic permafrost soils, and that another 600 billion metric tons are sequestered in deep permafrost. For comparison, human activities in 2019 released approximately 12 gigatons of carbon into the atmosphere, almost all of which was carbon dioxide, a point we will return to in just a moment. And more than 400 gigatons of carbon have been released cumulatively into the atmosphere since the mid-1800s by anthropogenic activities. Climate change and disturbances across the Arctic are causing permafrost to degrade, such as in this massive retrogressive thaw slump from the northern Alaska region, which extends nearly 300 meters from the river up to its head wall on the slope. Current best estimates are that as much permafrost may thaw by 2100. This would reveal the organic carbon that had previously been in the frozen ground. Here we see an image of thawing permafrost as it oozes and drips, and I must admit that it has a rather foul odor. The risk to them is that if even a small amount of this carbon stored in the near surface permafrost, 0 to 3 meter level, were converted by microbes into carbon dioxide or methane and then released into the atmosphere under the so-called permafrost carbon feedback, it would act as a major negative perturbation to the climate system. For example, only 9% of the 1,100 gigatons of near-surface permafrost carbon were converted into carbon dioxide or methane, then this would amount to nearly 100 gigatons released and become comparable in magnitude to the anthropogenic emissions that had been released since 1850. Furthermore, these natural emissions would occur during a period when the international community is trying to achieve zero carbon emissions or even negative carbon emissions targets. Methane emissions from permafrost thaw are even more damaging, since they have approximately 30 times the radiative forcing impact of carbon dioxide emissions on a 100-year timescale. Therefore, it is critical that we understand everything we can about the permafrost carbon feedback, particularly its methane fraction. However, our current standing of methane permafrost carbon feedback is uncertain, and we not project the permafrost carbon feedback with confidence. We do not know where the carbon will be released. We do not know when it will be released. We do not know amounts of carbon, how fast they will be released, or in what form the carbon will be released, whether carbon dioxide or methane. The need to significantly reduce uncertainties surrounding Arctic methane emissions and permafrost carbon feedback were the genesis of the Methane and Permafrost Challenge. It was conceived by NASA and ESA and rolled out in December of 2019, just before the pandemic changed everything. The objectives of the Arctic Methane and Permafrost are shown here. In this artistic rendering of permafrost, we see a cutaway of underlying Arctic tundra, wetlands, and the boreal forest. The active layer is a near-surface layer of soil that thaws during the warm season and then refreezes each winter. It's typically 30 to 100 centimeters in depth. Permafrost is the perennially frozen soil. Talik are soils that remain thawed year-round despite being within the permafrost zone. Taliks are frequently found beneath lakes where year-round heat content is transferred from the surface to depth efficiently. In fact, the oxygen-free environments in thawed permafrost beneath lakes is ideal for generating large amounts of methane or for providing escape routes for geologic methane reservoirs that were previously capped by frozen permafrost. This video shows the seething cauldron methane ebullition from Isay Lake in northwestern Alaska. This is the largest terrestrial Arctic geologic seep that has been characterized to date. You can see directly over the seep the very massive ebullition. Work done by Professor Katie Walter Anthony and her group from the University of Alaska Fairbanks has quantified the methane emissions by placing portable flux chambers down over interesting features on both land and water to quantify the rate at which methane escapes to the atmosphere. These chambers need to be tall so as not to disturb aquatic vegetation, which acts like giant straws and provides a methane autobahn from the root system beneath the water to the surface, as opposed to the slower diffusive pathways that ocean bubbles follow through the water. Bubbles trapped in the ice. Here's an image which shows methane bubbles trapped in winter lake in Siberia. Professor Walter Anthony and her group pioneered a technique to use space synthetic actuators to determine bubble density in ice, and then use this to estimate methane flux from lakes. This allows one to measure emissions from thousands of lakes at a time and estimate aquatic methane emissions, in principle, across the entire Arctic. The launch of NISAR, the NASA Infrastructure Radar mission in 2023, will enable Arctic lake methane emissions to be quantified and the timescales, provide unintended insights to the aspect of the permafrost carbon feedback. Similarly, researching NASA's Arctic Boreal Vulnerability Experiment, or ABOVE, has exploited of terrestrial methane hotspots using air perceptual imaging from the AVIRIS Next Generation sensor. AVIRIS-NG flies along, making its measurements at approximately 5-meter scales over transects that are 10 to 100 or more kilometers in length. In this image, we see a composite map of many AVIRIS transects made over the Mackenzie Delta region of Canada's Northwest Territories. Each of the white dots represents an individual 5-meter by 5-meter pixel in which methane was detected in enhanced amounts, more than 5 standard deviations larger than the mean value. If we zoom in on the upper right-hand side, we can see methane at the local level, where distances are measured in kilometers. And on the lower right-hand side, we can see at the landscape scale, where distances are measured in tens to 100 or hundreds of meters. We can characterize the hotspot distributions across all of these scales and develop increased appreciation for the statistical of methane across multiple scales. NASA and ESA are developing the surface biology and geology and CHIME space-based hyperspectral imaging missions to be launched in the mid to late 2020s. These instruments will allow us to extend terrestrial methane detection techniques to the entire Arctic and to monitor interannual to decadal scale changes in terrestrial fluxes in much the same way that the SAR sensors will allow us to monitor aquatic fluxes. The AMPAC team are examining ways to exploit these and other satellite data streams to better characterize and quantify permafrost and the permafrost carbon feedback. Here we summarize AMPAC activities and some near-term plans and highlight 3 recent synthesis papers. About international participation and encourage interest to contact us about ongoing projects or learn more below. Thank you very much for your attention, for your interest in Arctic climate issues, and particularly for the opportunity to tell you about the impactful research and synthesis activities being undertaken by the NASA-ESA Arctic Methane and Permafrost Challenge team.
All right, thank you, Chip. So that concludes our side event that discussed U.S. contributions to Arctic research applications and decision support. And I want to thank everybody that joined virtually and in person. And I hope you all enjoy the remainder of the COP26 meeting. Thank you so much.